Okay, so good evening, everyone. We'll start today's session. So, first of all, I guess it's been a long duration that you have gone through this control engineering course. Do you have any feedback to give about it? How was the course? Which were the interesting parts? And how did I help you if I did? Or did I make it more troublesome for you? Any feedback? Okay, just those of you who are present, can you please type on the chat which week's like content was the most interesting one? Which subject, topic? Thanks for being so generous. 1, 2, 5, 6. Okay, 1, 2 was the initial topics, I guess. What was 5, 6? Week 5 and 6, right? Uh, I guess it was something to do with the time or frequency response. Okay, so we'll move ahead with today's questions. So today basically we'll be dealing with topics centered around state space models and how to control them, that controllability stuff, and how to design controllers and all. Okay, so with that, we'll start for today. So, first, consider this state space system given to us: A matrix, B matrix, right? Find the eigenvalues of A and its corresponding eigenvectors. So, can one of you tell me how do I find out the eigenvalues and vectors of a given matrix? This 2 cross 2 matrix here, for example. What is the definition of an eigenvalue and an eigenvector? Okay, so basically, if we have something like this, then lambda is called the eigenvalue, and the x that satisfy these things, they are called the eigenvectors. So to solve for the eigenvalues, what we do is we take the determinant lambda I minus a equal to 0, solve for lambda, then plug it in this equation, and then find all possible x that satisfy the given condition. So let us do lambda I minus a. Yeah. So what is the determinant? Is lambda minus 1 into lambda plus 1 minus of minus 5, sorry, into 0. That is equal to 0. So clearly lambda equal to plus minus 1 are the eigenvalues. Now look at this matrix. You can see that the diagonals are 1 and minus 1, and this is just an off diagonal element with the other part 0. So when you have some structure like this, you can say that the diagonal elements are eigenvalues, because when you take the determinant, only those things come out, rest terms are 0, right? So these are the eigenvalues of the matrix A. Now how do we find out the eigenvectors? Right, so let's take first lambda equal to plus 1. Or basically we want to find out the null space of lambda I minus a, right? So lambda I minus a, let's find out for lambda equal to plus 1. It is 0 minus 5, 0, 2, right, into x, which is something x1 x2 equal to 0. So what x1 and x2 satisfy these? So the two equations that we'll get from this set of two simultaneous equations, right? Any matrix Ax equal to 0 means what? It is a basically a set of n simultaneous equations in some number of vectors. Like if A is an n cross m matrix, then this is writing Ax equal to 0 will have this is m cross 1. So this is essentially n simultaneous equations in m variables, right? So here what do we get? Minus 5x2 equal to 0 and 2x2 equal to 0. So clearly x2 equal to 0 and x1 can take any arbitrary value that will satisfy. So as a basis, we can take 1, 0 as the eigenvector corresponding to this eigenvalue, right? Is it clear till now how we found out everything? Okay. Now I want to do the same for lambda equal to minus 1, and I'll plug in values in lambda minus a, that is minus 2, minus 5, 0, 0, right? So here the only equation that we'll get is 2x1 plus 5x2 equal to 0. So 1, like the set of vectors, basically the space of vectors that will satisfy this will be given by a basis of this kind of form. Is that correct? Can just anyone confirm if I am audible? Just a yeah, yeah, yeah. Thank you. So this is the second eigenvector corresponding to lambda equal to minus 1. So now, okay, so basically the eigenvector matrix is this, and the corresponding diagonal matrix formed by eigenvalues is this, right? So for this question, we wanted to find out the eigenvalues and its corresponding eigenvectors for the given matrix A. So that we are done with. Any doubts till now? No doubts? Okay. Now we want to find out the state transition matrix. So how do we do that? E, sorry. For a given matrix A, state transition matrix, that is for linear systems, is given by e to the power A t. Right. So I think we saw something of this kind in last class, where we discussed why we go for diagonalization, because it helps us in finding this exponential of the matrix, right? Because e to the power any a is given by this infinite series, right? But for any general matrix, if there is no special form or compactness to it, we cannot find out this infinite series every time, right? So what we do is, given any matrix A, we try to diagonalize it, so that if we get to a diagonal form through a similarity transformation, then that diagonal matrix e to the power d is again given by this series. But it so happens that if you have elements only in the diagonal row, or just one that in the Jordan block format, then what happens is the exponential of this matrix is just the exponential of the individual elements, right? So that is why we want to diagonalize the matrix, like find a similarity transformation to diagonalize it, and then find the exponential state transition matrix through that. So e to the power, we know A is equal to V dV inverse, right? Or D is equal to what is this? V inverse AV, where D and V are these matrices. Yeah. Basically, the eigenvector matrix provides a similarity transformation for a given matrix to get converted into its diagonal form, right? So e to the power at is equal to v e to the power dt v inverse. This we solved in last class how we can get to this result, but it's simple if you write this term as this infinite series and this term as this infinite series, you'll see that the both are same. So now let us find out e to the power at, right? So clearly d is just 1 0 0 minus 1, right? We obtained that. E to the power dt is e to the power t, e to the power minus t, 0 0. Then we want to find out v and v inverse. V is given by 1 0 5 minus 2. V inverse is given by can someone help me with this? Finding out the inverse. Just plug it into your calculators and give me the value. I'll wait for a few minutes. Yes, give me the inverse of this matrix, the V matrix written here. Come on, anyone? One zero minus 2.5 minus 0.5. Hmm, I think this is a bit wrong. If you multiply, acha, 0 minus 2.5 this. Okay, but if you multiply V with V inverse, these two rows and columns, does it come to 1? No, right? Just check once if you have made a mistake somewhere. Let's do it here. Right, so determinant is minus 2, right? Yeah, and the inverse is 1 minus 2. Yeah, this thing, something like this, right? Mm. Oh, sorry. Yeah. Minus 2, 1. So this is 1, my 2.5, 0 minus 0.5, right? Just check once. 1 5 is 1, This is yeah, 0. This is 1. Sorry, this is 0 and this is 1. Yeah, correct. So V inverse is this. V is this. Okay. So we have obtained V and V inverse. Now what do we want to find out? E to the power dt also we have obtained. So simply e to the power at is V e to the power dt V inverse. Correct. So 1 0 5 minus 2 e to the power t 0 0 e to the power minus t, and into this one 2.5 0 minus zero point 0.5. So go ahead, try this and tell me what you get. Let's do it. Mm, let's multiply these two first. So it's 40 5 e to the power minus t 0 minus 2 e to the power minus t. This is e to the power t. Yeah, this is what we get, right? And notice here that since the matrix A is itself in some kind of a Jordan block form, right? If you just get a factor out, 1, then this is in the, yeah. So this is in the kind of a Jordan block form, right? So that is why you can see here also, when you take the exponential, the diagonal terms are there, and only that one thing gets a little modified in terms of these two, right? Although it is not exactly what you would want in a from a Jordan block, but still, this lower triangular thing is always 0, right? Okay. So what did we want to find out for this question? Given this A, we wanted to find out the state transition matrix, right? E to the power at, and this is that e to the power at. Yeah. Is it clear till now? Okay. So now, without any control input, is the system stable? So let's see. A was, what was A? Yes. Si minus A inverse. Yeah. You can use this as well. Yes. Yeah, you can use this. Yeah. Yeah. So then we have 1 0 5 minus 1, right? So without any control input, that is u is 0, the system will just be x dot equal to ax. So tell me whether this system is stable. How do we know whether a given linear system is stable or not? Whether a given autonomous linear system is stable or not. So how did we know it in a CISO case? We basically saw where the poles were located. So here also we'll do something similar and check out where the eigenvalues are located, right? So for this matrix, we know that eigenvalues are 1 and minus 1, plus 1 and minus 1. Clearly, this one is an unstable eigenvalue because it is plus 1. Basically, you know that when you write the transfer function, in the bottom we'll have the determinant of si minus a. That thing comes, not determinant like that. Yeah, the determinant, the polynomial will be determinant of si minus a. And so this equal to 0 basically means the roots of s are the eigenvalues of a. So if one of the eigenvalue is in the is positive, that is greater than, strictly greater than 0, then this system will be unstable, right? So the system without any control input is unstable, right? Is it clear till now? Yeah. Okay. So is the system controllable? And if not, is it stabilizable? So how do we check whether the system is controllable or not? Yes. How do we check whether a given linear system is controllable or not? Anyone? You are given a system x dot equal to ax plus bu. How do I check whether this dynamical system is controllable? So we have something called a controllability matrix, right? Given by b, ab, and so on till e to the power n minus 1b, where n is the dimension of the system, right? So for this n equal to 2, so we'll just have c equal to b and ab. Remember, A is given by 150 minus 1, B is 10. So this is 10 and AB is, we can find out, 1 and again 0. Yeah. So this is the controllability matrix. Is it clear till here? Yeah. Okay. So then further, how do we know whether the system is controllable from this controllability matrix? A given linear system is controllable if rank of C is full, that is equal to the dimension of the system. So here, what is the rank of this matrix? Yes, anyone? What is the rank of this controllability matrix that we found out for the given system? Okay, so how is the rank 2? Yeah, n equal to 2, correct. But we say that if this is the case, then the system is controllable. But rank is basically defined as the number of independent columns that you have in the matrix, right? And this first column is 1 0, second column is also 1 0. Clearly, these two columns are not linearly independent. So the rank is not 2, but the rank is 1. Rank of this matrix is 1. So the system not controllable. Okay. Okay. So so then this is clear. The system is not controllable. Next, what we want to find out is, so whether the system is stabilizable. Now to find out whether the system is stabilizable, what we need to do is we need to use some kind of a similarity transformation such that the matrix A in the new coordinates gives us some A tilde which is in a form such that here we'll have controllable eigenvalues, here we'll have something A, C, A1 to 0, and here we'll have the uncontrollable eigenvalues, right? So then we'll see, and B tilde will essentially be 1 0, I guess, yeah. And then we'll see, these are the controllable eigenvalues, so we do not care what those values are. We can place them appropriately wherever we want by the help of giving a control. But these are uncontrollable. So what that means is, no matter what, we cannot shift those system poles to anywhere else. So these uncontrollable eigenvalues must be stable. If that happens, then what? Then the system is such that the uncontrollable eigenvalues are stable ones, and the other ones, which might or might not be stable, are controllable. So we can place them in some stable region. So overall, the system can be told as stabilizable, right? So to get this similarity transformation, what we'll do is we'll write some z equal to px. Okay, so then what happens is x dot equal to ax plus bu. That becomes, write x as p inverse z. So here we'll have p inverse z is equal to a p inverse. Just a minute. Let's shift this. Let's take x equal to pz such that z equal to p inverse x. So here what we'll get is x is pz dot equal to apz plus bu. So this gives me z dot equal to p inverse apz plus p inverse bu. Right, this is a similarity transformation, basically change of coordinates. We came from the coordinates x to the coordinate system z, kind of. And then what transformation p should we take? For that, what we'll do is we'll take the linearly independent columns of C, 1, 0, and then fill the rest such that that is also linearly, like such that this entire matrix becomes linearly like full rank. So a great simple choice is the identity matrix, because here these two are same. I can fill this one as I want arbitrarily such that P is full rank. Now this A tilde and B tilde. So A tilde is P inverse AP. So what is that? 1, 5, 0 minus 1. Like, because P is just the identity matrix. So A tilde is just A and B tilde is also just B. So now again you see that this system is already in this decomposed form. So essentially this one is the controllable eigenvalue, this one is the uncontrollable eigenvalue, and this is just an A12. So the controllable eigenvalue E value is 1, uncontrollable E value is -1. So what did we discuss? If the uncontrollable eigenvalue is negative, then we need not worry that the system will go unstable, right? Because see here, the controllable eigenvalue is unstable, but since it is controllable, we can place in appropriate control to shift that eigenvalue location to the negative side. And the uncontrollable eigenvalue on the other hand, it is stable. So basically the entire system is stabilizable. Stabilizable system. Yeah. Is it clear till now? Okay. So this is how you find out whether a system is controllable and further whether it is stabilizable. Then find the transfer function of the system and comment on it. Okay, so I forgot what was the ah I think okay, let us assume some C value x plus 10 u a b and y is equal to cx plus du. So tell me what should the transfer function of the system be in terms of a b c d y of s by u of s. What should this be? Come on, anyone? Okay, so this is given by C Si minus A inverse B plus D. So A and B are given. We just have to see, let's say C is 1, 0 and D is 0. Okay, so this one we'll get 1, 0 Si minus A inverse B. Okay, so what is this? This is, we have, let's find the determinant. This determinant is this. So this is 1 by S minus 1. Then this entire thing becomes, so look at this. The entire transfer function of this entire system boils down to just this thing. Now what is the pole of this? The pole is s equal to 1. But that other pole, the s equal to minus 1, yeah, that pole did not that eigenvalue did not appear in the denominator of the transfer function. Why? So what happens is, when you have a system with some controllable modes and some other uncontrollable ones, then what happens is only the controllable parts, they get represented in the transfer function, and the uncontrollable eigenvalues, they do not. Right? So that is what you see here. 1 by s minus 1. Only the s equal to 1 pole, which was controllable, that appeared in the system, while this one, the uncontrollable one, that did not appear in the system. Right? Is it clear? Okay, we move on ahead. Now consider u equal to minus kx. Okay, let's take that. A u is minus kx, so what will happen is x dot equal to a minus bk x, right? So a minus bk is 150 minus 1 minus 10 k1 k2, so that is, This, right? Yeah. So this is the matrix. Now we want the eigenvalues to be at -1 and -1. So we find the eigenvalues of this matrix. So lambda I minus A plus BK. That is lambda -1 plus K1, K2 minus 5, 0. Yeah. Now we want to find this determinant and equate it to 1, equate it to 0. So again, this part is 0, this cross diagonal, and the other one remains. Right. So what are the eigenvalues? They are -1 and this is 1 minus K1. So look at this. One of the eigenvalues is -1. It does not depend on what controller we use. So this again confirms the fact that this -1 eigenvalue, that was the uncontrollable one. Right? No matter what control we give, we cannot affect its position. That will stay there. But on the other hand, the other eigenvalue that we had, +1, that can be altered by this controller parameter. So 1 minus k1. Now we want both the eigenvalues of the closed loop system to be at -1. So clearly we can choose k1 equal to 2 and k2 can be anything arbitrary. We can just put it at 0. So the desired controller is -10x. This will put the system, the closed loop eigenvalues both at -1. Right? Yeah. So we are done with that first problem. Is it clear till now, whatever we did? Yes. Is it clear? Okay. We'll move on ahead. Now consider this three-dimensional system x dot equal to ax plus bu, where a and b are given as follows. When using Ackermann's formula, find a state feedback controller K such that the control law U equal to minus Kx places the closed loop poles at the desired places. Right. So if we remember the Ackermann's formula, it is given by K, this capital K is given by 0, 0, 1 C inverse phi d of A, where C is the controllability matrix and phi d is the characteristic equation. Basically, the take the determinant of Si minus A and substitute S in A in terms of S. Basically, S minus A, this equal to 0. This polynomial that you'll get, substitute. I'm sorry. Yeah. Now, okay. Let us first find out phi d of A. Yeah. Sorry. My bad. So phi d of A is basically the desired closed loop pole location. We want the closed loop poles at this. So this is phi d of S. Now here for phi d of A, we just substitute A in terms of, right. So we'll use MATLAB for this particular problem, but the process is entirely same. Just give me a moment. I'll open MATLAB. Yeah, okay. So can you see my screen? Yes, can someone just respond? Is my screen visible? Okay. Yeah, thanks. So A and B we have. Now we want to find out the controllability matrix, right? So what is the controllability matrix? It is given by B and A into B. And since this is a third dimension, into B, right? So this is the controllability matrix. I'll just write it down. Give me a moment. So then, if I find out, given that formula, 0, 0, 1 into, this is the K matrix, into C inverse into the phi d of A, which is A plus 1, A plus 2 into A plus 3. So this is what we get. The desired controller is given by these values. Minus 158. Let's write it down. Give me a moment. Yeah, yeah. Is it correct? Yeah, it should be correct. Right. So is it clear what we did here? We wanted to find out a given state feedback controller using the Ackermann's formula. So this is what we get. Okay. Then just a moment. 0, 0, 1. Yeah, cool. So I'll then share this. Okay. We are done with this. We were given A and B. We found out the controllability matrix. Then using the Ackermann's formula, we find out this. Now, although we did it in MATLAB, like it is not conceptually any different, it's just computationally easier to do with it. But you can do the same thing with your hand or calculator. Then, using a similarity transformation, convert this system to its controllable canonical form. So, such a similarity transformation is given by z equal to, one moment, z equal to tx. So here what we'll have is z dot equal to t a t inverse z plus t b u. This is the new system. So this is a tilde and this is b tilde. Now the desired transformation that will convert this given state space system to its controllable canonical form. For that, the transformation is given by q q a q a square, where where q is the last row of C inverse matrix. Okay, so C matrix you had here, this one, then you will take the inverse of it, find Q, then get this similarity transformation, right? A tilde and B tilde. Okay, so let's do that again on MATLAB. So here we have, what do we need? So first we want to find out that inverse of the controllability matrix, inverse of C. So let's just note it down. Give me a moment. Right? And this last row, that is the Q thing. Okay, zero point 0.5 minus 0.5 minus 1.5. So Q is C last row. Sorry. We have to, Q is the C inverse. Q is the last row of this. Okay, zero point 0.5 minus 0.5 and minus 1.5. So the new transformation is Q into Q into A square. So this is the transformation matrix. Let's again note it down. Give me a moment. Yeah. So we have found out T now. Now all that remains is we want to find out A tilde, which is T A T inverse, and B tilde, which is T B. So if we find out T A T inverse, so here you can clearly see that this A tilde is in the desired canonical form representation, 0 1 0 0 0 1 and so on, and only the bottom row has some elements, 6, yeah, and B tilde also we can verify, which is nothing but TB. This is again just 0 0 1. So now we have the system in its controllable canonical form, correct? So is it clear what we did till now? Screen. Yeah, okay, I'll just go over the process on the writing part. So see, we have a system of this form, okay? We want to find out a transformation like this, all right? That, and this transformation will convert it into the canonical form. So that T is given by this form QA square, where Q is the last row of the inverse of the controllability matrix. Okay, yeah. So you find out this T, then the new controllable like matrices, like the transform system is just TAT inverse and TB, which you can see it is clearly in the standard controllable canonical format. Alright, so this is how you do it. Then using the controllable canonical form state space representation, find a control log K that places the closed loop poles at -2, -4 and -5. Okay, we had, what do we have? A tilde is 0 1 0 0 0 1 and sum minus a3 minus a2 minus a1. So this basically means the what do we say? The eigenvalue, the determinant of this Si minus A tilde is given by, this is a well-known fact. So we just want to compare this. Okay, just a minute. So now when we add u is equal to minus kx, what we'll have is z dot is equal to A tilde minus kz. Z dot is A tilde minus B tilde K Z, right? So we want to, what do we want to find out? We want to find out the desired K. Now let's just see what this thing is. This thing is of the form 0 1 0 0 0 1 minus a3 minus k1 minus a2 minus k2 minus a1 minus k3. Okay, this thing. So this, the eigenvalue equation will be equal to 0, right? Now we want the poles to be here, so the desired polynomial that we want is this. Okay, so this is s squared plus xs plus a. Yeah, so this is the desired polynomial, so we'll just compare coefficients with this. So a1 plus k3 is 11, a2 plus k2 is 38, and a3 plus k1 is 40. Now we know from this, where was that? This is minus a1 minus a2 minus a3. So a1 is 6, sorry, minus 6, a2 is 13, and a3 is minus 14. Right? So this means k3 is 11 minus a1, so 17. K2 is 38 minus A2, which is 25, and K1 is 40 minus A3, which is 54. So this is the desired controller, and when we have the system in the controllable canonical form, right? So is it clear what we did today? Yeah. So today we basically discussed systems and how, if they are controllable or stabilizable, and how to determine all those. Then given systems in their regular forms and controllable forms, how do we control them? How do we place the eigenvalues in our desired locations, right? So with that, if it is all clear, then maybe we can wrap up today's session. Do you have any doubts, or should we wrap it up? Okay, it seems we can end the session. Thank you for attending.